Hello and welcome to the presentation. I am Jaideep Shen from IBM India Research Lab, and today I am going to present our paper Optimizing Interpretation Generation in Natural Language Query Answering for Real-Time End Users. This work has been co-developed with my colleagues in IBM India Research Lab. So as the title suggests, this is dealing with natural language question answering. So we'll start with the introduction of NLDB systems, which is kind of the context of this problem. And NLDB system stands for Natural Language Interface to Database, where a user asks a natural language query that gets interpreted by considering some domain semantics, and it gets executed over a backend data store to finally give the user some JSON response in form of UI, or may even with a raw JSON response. So this is the spectrum of NLDB query systems. We will also start with some background so that we can appreciate where the work is coming from. And one of the things that I want to cover in the background is ATHENA, because the paper is experimental on that. It was a state-of-the-art NLDB systems which was proposed by Dipti Kalyan, Saha and company, and it was presented in FieldDB 16. So just to give you an architecture of this ATHENA paper, there is an NLQ engine which takes into consideration the domain semantics by a domain ontology that is designed to capture the domain semantics, and it also uses an index, an inverted index, to really know the actual database values that appears in the database. And using that, it tries to interpret a query. It goes through a two-phase approach. It tries to interpret the query on top of the ontology first, trying to form an ontology query language, which is abbreviated as OQL, which get translated finally to our target query language like SQL. The key point here is domain ontology is a plugin for this architecture. So it kind of captures the domain semantics. So we will just zoom into how an ontology really looks like. So this is an example ontology. It's a finance ontology snapshot. And as you can see, there are different concepts related to different parts of finance, like company, lender, borrower, commitment. They together model that lending relationship. A different set of concepts like company, banking metrics, banking subsidiary, they together model like financial metrics for bank. So an ontology you can think of like it is distributed to different domain functionalities it's trying to capture. So now let us see what is the challenge of natural language interpretation and why the precise interpretation generation is really something which is important. So let us take this example query, what are Caterpillar loans since 2012. So in this example query, if you enumerate what are the individual tokens might possibly mean in the context of the ontology. So Caterpillar has 5 possible meanings. In the sense that Caterpillar has appeared in the database as company name, as lender name, as borrower name, investor company name, investee company name, and so on. Similarly, since 2012, it's just a date mentioned, but there are like 18 date properties in an ontology. So it can be either any of those if you just consider the phase since 2012. So what happens is if we try to really consider all the different possible interpretations out of the query, we need to consider the Cartesian product, which is like 170 candidate interpretations. Now, clearly, not all the interpretations are kind of equally likely. Not even they are not even valid. All the interpretations. If you really see, the intended interpretations are these two interpretations, where Caterpillar is either the lender name or the borrower name, because the question is asking for loans. So what happens is in a typical NLDB scenario, such kind of ambiguity is very relevant in large ontologies. So it kind of wastes a lot of CPU cycle. Needless to say, this makes the real-time question answering kind of risky for real-time end users. The academic setup kind of considers going back to the user to disambiguate which of these choices is a real choice, but that might not be an ideal industrial solution because it kind of prevents you from having a one-shot QA experience, like user just calling REST APIs and getting the response straight away. So that's why it becomes an important problem. Now, for solutions, we will basically review 2 solutions. One is functional partitioning and one is lazy inclusion. Let us see what they are. Functional partitioning, this was actually a paper which was first proposed by, again, the same authors. We proposed this paper in Ichkai 2018. The idea of functional partitioning was to basically view the ontology as a collection of different domain functionalities and partition it that way. To define it mathematically, we defined a relationship called uniquely identifies. And the idea of uniquely identifies relationship is if a concept, if an instance of C2 can be uniquely identified by an instance of C1, then C1 and C2 is in uniquely identified relation. So just taking an example, consider this functional relation from loan to borrower. So there can be n number of loans for a borrower. In this case, a loan instance can uniquely identify a borrower who really took that loan. But a borrower cannot uniquely identify a loan because the same borrower might be involved in different loans. So the uniquely identifies relation is between loan and borrower, not the vice versa. And that's where arity becomes important. The n is to 1 arity here kind of gives the hint that where the relationship should go. But this also is a central theme for computing functional partitioning. So this is just I have still kept the slide here uh, where the functional partitioning really revolved around using the exploiting the arity with different rules to create components. But more importantly, we will jump towards a sample picture, sample figure. So this is a sample finance ontology snapshot, and once we apply functional partitioning to it, you really see the different components comes out. So there is a component for investment, considering the concepts investor, investment, investee. There is a different component for loan with concepts lender, borrower, loan agreement, commitment, and so on. So all the different domain functionalities kind of gets partitioned into different components. Now let us see how do we want to use it for real or solving the real problem that we have. Again, it's the same question that we are considering, but now the idea is we want to cover all of the query tokens using minimal number of partitions as possible. And if we try to make sure that we are using as little as less number of partitions, then there is only one candidate here, the loan partition. It can actually accommodate all of the tokens. So that means even the caterpillar had 5 different choices, but from loan, there are only 2 choices for it. And therefore we arrive at the right 2 interpretations that we wanted. Same thing happens for since 2012. It gets nailed into the single choice loan agreement date. The second idea is lazy inclusion. Here, the problem is again the same, but we kind of differ the choice or this mapping for ambiguous tokens until other more or less which are non-ambiguous tokens are settled. So what happens is out of the 3 tokens, Caterpillar, loans, and since 2012, loans is still relatively having less number of choices. So it is kind of non-ambiguous. So loans get matched to 2 possibilities that it has. Now, after that, our idea is for ambiguous tokens, then we try to select the closest matches to where the non-ambiguous tokens are, no tokens have settled. So that means for loans, the 2 possible choices are lender, because that is closest to loan commitment, or borrower, which is closest to loan agreement. And in this way also lender basically the token caterpillar basically proves out the irrelevant choices and settle down to the choice which gives the most compact size. Same thing happens for the time trace token as well. So for the experiments, we used 3 standard datasets: finance, software, institution, they are publicly available ontologies. The question set was so chosen such that they are typically ambiguous in nature. They are hard to disambiguate without talking back to the user. The second table also kind of gives a ray of hope, because if you really see, most percentage of even the ambiguous queries can be contained in one of the unique components. So that kind of means that why this partition based approach might work or should work. So this kind of matches with our intuition. For matrix, we wanted to count the average interpretation count, which is the basic thing, how we want to measure that, how precise we are in generating different candidate interpretations. Correlated with that is average interpretation time. So these are the main metrics where we are expecting improvement. But more importantly, we want to make sure we are not losing precision and recall in trying to improve AIC and AIT. So let us see how the result pans out. So clearly you see the AIC for and AIT, both results are kind of correlated, which is kind of expected. For both partition and lazy inclusion, both of them kind of significantly reduces the number of interpretations. But partition typically works better than lazy inclusion, and this probably can be explained by the fact that partition takes more of a global context view. It considered the whole question to figure out what should be the right partition, whereas lazy is more towards local context, depending on what are the other tokens where they have settled, and it tries to go towards that side. But invariably, both of them kind of works in all the three benchmarks, and uh, partition does just better than lazy most of the time. The table 5, which also makes sure that precision and recall is intact, it's like above 90, which is reasonably good. That means we are not really sacrificing precision and recall. We are able to hold on to the right answers, but significantly reduce the ambiguity in processing those. So to conclude, we proposed two novel ways how to deal with ambiguity in generating interpretations. Although it is tested with ATHENA, but it's not very specific to ATHENA. These techniques can easily be applied to anywhere else as well. And we actually experimentally show that it does a huge improvement on interpretation counts and time. And this is a relevant solution for the industry where it is still fine to give the user that feeling of one-shot QA. For future work, we want to utilize the functional partitioning idea more for other semantic reasoning problems as well, including ontology alignment or query recommendation. And the other part is we also want to utilize query logs in conjunction with functional partitioning, trying to learn this automatic disambiguation in a better way. So this was what we wanted to cover. Thank you for attending our presentation. We'll be happy to take any questions. Thank you.